Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, May 21, 2021. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a balmy moonlit evening in Rockport, Massachusetts. These Earth and Space Reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environment, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. Today, we are joined by members of the Rockport Research Explorers, Rockport Cultural Council, Gloucester Area Astronomy Club, and other curious folk. Thank you for coming. This evening, I will be talking about different ways of mapping and understanding our home galaxy, the Milky Way. So let's get to it. First thing I do is share my screen. You get to see my emails. And then we move to PowerPoint and slideshow. Okay, all set. So the title of this presentation is called Surfing the Galactic Froth. And so I looked around for good examples of surfing, and I came up with Snoopy. And the galactic froth is clearly evident in this picture of a small piece of the Milky Way. It's a 60 degree by 60 degree piece of the Milky Way, showing all sorts of frothy something or other. Okay, so first I'd like to give many thanks to my colleagues on this work, and they include Francois Boulanger in France, Frank Verosi in Florida, Bill Wall in Mexico, now retired in Vancouver, who's here on this presentation, and the Caltech Infrared Processing and Analysis Center, and finally NASA's Goddard Space Flight Center, all of which made all of this possible. Wouldn't have been possible without all these folks. Okay, so you've heard of the Milky Way, but what is it? Check. It's a candy bar. It's a very good candy bar. And if I teach the Milky Way, I make sure to get some Milky Way candy bars for the students. It's also a faint band of ghostly light in the sky. Check. It's made of stars, gas, dust, dark matter, most likely. Check. And it's also our home galaxy. So the Milky Way is both an apparition, something you can see in the sky, and an object. It's a galaxy. So if I was in a class, I would be asking how many of you have ever seen the Milky Way. Well, I'm not going to go through the polling, but I would make a prediction that about 25%, 30% of you have actually seen the Milky Way with your own eyes. Perhaps with this enlightened crew, it would be more, but I've asked students at Tufts University in an urban center whether they'd ever seen the Milky Way with their own eyes. And I've asked students here in Rockport at the high school how many, and invariably get around 25% to 30%. But it's there for the viewing. All you have to do is get to a dark sky without light pollution and without the light of the moon. The reason why most of us don't get to see it is that we are in light polluted areas. And here is an example of a place in Ontario, Goodwood, Ontario. And this is what would be typical, where you have lots of glare bombs from lamps that are poorly shielded and poorly directed. And this is before a power blackout, and this is during a power blackout. And I think during this power blackout, there were calls to the authorities saying, what are these things that I'm seeing in the sky? You know, should I be scared? So many people do not get to see their galactic birthright, which is a bit of a shame. Okay, but if you do get yourself to a very dark sky, and there are these dark sky oases, and they're increasing by the minute to ward off the ever-increasing light pollution, you would see a dark sky like this. Well, I mean, this is an exceptional dark sky. This is on top of Cerro Tololo Inter-American Observatory in Chile. And it's a long camera exposure, but you can see this with dark adapted eyes. It's pretty impressive. And first off, this is a companion galaxy. We're in the southern hemisphere. This is the Large Magellanic Cloud. And this is another companion galaxy, the Small Magellanic Cloud. So they're like dwarf galaxies compared to our Milky Way galaxy. Our Milky Way galaxy itself can be seen running diagonally here. And there's some objects that would be worth noting. There's Alpha Centauri, which is the nearest star to us, 4 light years away, and Beta Centauri here. There's Crux, the Southern Cross, which is on so many flags, including those of Brazil and Australia and New Zealand. And then here's the Coal Sack, which is a dark region, which we now know is due to a cloud of obscuring dust. Okay. Here's a rendering which I like. It's by Wally Pacholka. He has a copyright, so I have to make sure I say it. And it's a view of Devil's Tower, National Monument in Wyoming. And it's a very wide angle view, so you see the Milky Way arcing across the sky. And you can see it's got lots of interesting details, star clouds, lots of stars, also regions of darkness, which they didn't know what those regions of darkness were they actually holes in the firmament? But then E.E. Barnard noted on a particularly dark night in California that there were some foreground clouds, as we can see right here, and they were obscuring the light from behind, just like this sort of stuff here. And so he concluded that what we were seeing are clouds of gas and dust, and it's the dust that's obscuring the starlight from behind. So a very nice picture. Here on Cape Ann, we do get dark enough skies so that you can see the Milky Way. And in the summertime, you might be able to see something like this if you were on the southern side of the Milky Way. Southern side of Cape Ann, like around Good Harbor Beach, and you'd be able to see the star clouds of Sagittarius. And here's some foreground clouds again in our own atmosphere, obscuring what lies beyond. So why is the Milky Way such a big deal? It's, okay, it's an apparition in the sky, yada yada. But there are reasons for paying homage to the Milky Way, because just as it takes a village to raise a child, according to an African proverb, but it's also true that it takes a galaxy like the Milky Way, a big galaxy, to cultivate the stars, planets, and conditions necessary for complex life to emerge. So we have the Milky Way to thank for our existence here on this rocky planet, this moist rocky planet, going around a star which is fairly well behaved. Okay, so it would be nice to be able to see the entire Milky Way. So how could you do that? Well, you could ride a magic carpet to the stars, and what would you see? You have to get beyond the blinding sun, and you have to get beyond the Earth, because it obscures half of the sky. And if you could do that, along with J-Lo, and I don't know who this fellow is, and you would be able to see this. You'd have to get pretty far away, somewhere out in the outer reaches of the solar system. You'd be able to see this, or it would be a sky that completely enfolds you, completely surrounds you. This is a particular mapping of that entire sky. And this was actually done by taking pictures from the northern hemisphere here and from the southern hemisphere here, and stitching all these pictures together, as Axel Mellinger did. And if you arrange things right, you would place the plane of the Milky Way, along the major axis here. And the galactic pole would be here, North Galactic Pole, South Galactic Pole here. The galactic center is obviously here. It's there for the viewing. And you'd start your longitude here at 0, 0. And then you'd go to positive 90 degrees here, somewhere in the Cygnus area. And then you move on to about 180 degrees. You're now in the galactic anti-center. You're looking away from the center. And that's repeated on this side over here. And you go past the Orion star-forming region, past this Gum Nebula here, say hello to the large and small Magellanic clouds. I think these are this and this, I believe. And past the Coal Sack and Alpha Centauri and Beta Centauri. And you're back to 360 degrees or 0 degrees in longitude. So that's a full mapping of the Milky Way. And you can see that it's a busy place with starlight, lots of starlight, but also it's riddled with darkness, these dust clouds which obscure the starlight from behind. But nowadays, there are all sky mappings at other wavelengths, from very long wavelength, low frequency radio continuum to very, very high frequency, high energy, short wavelength gamma rays. It's the highest energy stuff. And so I'll just go through some of this because they all trace different parts of the Milky Way galaxy. The radio continuum traces electrons that are speeding around lines of magnetic fields in the Milky Way at relativistic speeds near the speed of light. And this big loop is probably due to a nearby supernova blast. The atomic hydrogen pervades the entire disk of the galaxy. It's the most abundant of the gases seen in the Milky Way disk. The molecular hydrogen is more discrete, more confined. It's traced here not by the molecular hydrogen itself, but by carbon dioxide, which emits more readily than the molecular hydrogen. The infrared, which I'll be focusing on here, traces the dust associated with clouds that have been warmed by stars within those clouds, newborn stars. That's in the far infrared. In the near infrared, you can see the stars themselves without the obscuration that you usually see in the optical and the visible. So you can see clear through to the galactic center. And that shows just how thin the disk of stars is. Here's the visible image, again compromised by the clouds of dust. But we have those clouds of dust to thank for our existence. So I'm not complaining too much. The X-rays are very high energy emissions from high energy gases in the millions of degrees. And the gamma ray is the highest energy emission, but it ironically is associated with some of the coldest material, back to the molecular gas, just because of how it interacts with the molecular gas. So, so we'll move on. Here is what I'm going to be focusing on. It's the far infrared view of the Milky Way. It's a mosaic. It took, I'd say, more than a decade to really get put together by the IPAC folk at Caltech and JPL. But you can clearly see that it's dominated by this line of emission. And then everything kind of falls off with galactic latitude. There are some things that are poking out here and there, the Cygnus star-forming region, but there is this intense mid-plane brightening. So I'm going to zoom in onto the central, oops, sorry. I'm going to give you a schematic first. So what are we looking at? And why is it so bright right along the center? Well, if you look right in towards the galactic center, you're looking through all this stuff, and it all adds up in the far infrared because the dust is glowing rather than obscuring at temperatures of a few tens of degrees above absolute zero. As you look off the galactic plane, you're seeing less and less material. And in fact, you're probably probing a much smaller piece of the disk. Okay, these objects right here are star clusters. So as far as the gas and the dust in the disk, you're probably just probing a small amount. And so that's why you see less and less emission compared to if you were looking in this direction. Okay. So let's focus in on basically a 100 degree by 60 degree area centered on the galactic center. For the amateur astronomers, they're very familiar with the constellation of Sagittarius, the teapot, Scorpius, the scorpion with his little stinger. And they're also familiar with some fun objects to observe through binoculars and telescopes, such as M8, which is the Lagoon Nebula, and there's actually an M20 right over here, which would be the Trifid Nebula, and M17, the Omega Nebula, and M16, the Eagle Nebula. And those are fun things to look at. But in terms of what's really actually going on, say behind the curtain, we're going to look behind the curtain now. And this is what you would see in the far infrared at a wavelength of around 100 microns. That wavelength is around the width of a human hair. And you can see that the midplane is just riddled with clouds of luminous material, courtesy of the stars that have been formed recently inside those clouds. And there's something going on here and something going on there. But you're kind of blinded by the midplane brightening. And so, but there's a trick you can do. And this is what we did, was we smoothed the emission in longitude, okay, but not in latitude. And then we took this image and divided it into the original image. And what you get are the residuals, the enhancements, the relative enhancements of infrared emission. And there's the froth. There's the froth. And you can see it's like a carpet, a Berber carpet. You know, the structuring goes all the way through the midplane. There's information at all latitudes. There seems to be, the power of the structuring seems to be constant at all latitudes. And that's something to pay attention to. You can see tiny little star-forming regions, clouds. They're probably on the far side of the Milky Way galaxy. This reveals those sorts of things. The Rho Ophiuchi region is shown very beautifully. There's a possible shell. You know, our human eyes start seeing patterns. There's a possible shell here. There's a possible shell here. I'm not going to argue the point. The Corona Australis seems to have curved edges, perhaps due to winds from stars in the area. We just don't know. But it's a glorious thing to behold and just begs further understanding. So I'm going to go back to this just to remind you, these objects, M8, M17, and M16. Let's see if we can find them. There's, yeah, M8, M17, M16. This might be M16. I'm not really sure. So yeah, there's a lot of goodies to examine. This is a great way to do finder charts. You know, if you were wanting to understand the biochemistry of star-forming regions, you know, what sort of molecules, these are the regions that you'd be looking at. Okay, let's move downstream towards the sun's direction of motion. We are moving down in longitude, and these are the late summer, early fall constellations of Cygnus, the Swan, and Cassiopeia, the Queen. That's circumpolar, and in fact, the pole star is right here. There's a lovely cluster, beautiful through binoculars, in Perseus here, and there's also the Heart and Soul Nebula, and there's a star-forming region in Cygnus. So what do you get with the infrared? The Cygnus star formation region is just ablaze with activity. There's something going on the way to Cygnus. There's this big cavitated region. One side of it actually has a name, IC 1396, and has been studied to some degree, probably could be studied some more. but this is an example of secondary star formation after something popped off in the middle, maybe involving supernovae. Again, we don't know. This is the Cepheus Loop, which is yet another cavitated region due to prior star-forming activity. And here's the Heart and Soul Nebulae. But the froth, you know, it's everywhere. It's ubiquitous, and it has interesting structuring. Looking towards the galactic anti-center, this is Perseus seen to the north, and the Heart and Soul Nebulae, and the Orion region, or a rich region with a kind of a shell of glowing hydrogen gas here because it's been ionized by the stars within, photoionized. Barnard's Loop, which I don't think you can see that with your eyes, even through a telescope. You need photographs. But there's the Orion Nebula here. And the Pleiades, which is a naked eye object, which is fun to test your eyes for how many stars you can see. And here's what we see in 100 microns. Perseus turns out to be a very busy place, busier than I had expected. And here is that shell of emitting hydrogen now seen in the dust. And then here is near the belt of Orion, the Horsehead Nebula region, and then the Orion Nebula region. So again, all sorts of frothy residuals, which we don't really know what's going on. The last place to look is looking upstream, away from the sun's direction of motion. And there's this big honking object. It's 60 degrees, I'm sorry, is it 30 degrees in size, I think? It's a big object. And it's called the Gum Nebula. And it's a hybrid of photoionized gas from newborn stars, plus the remains of supernova explosions. The most powerful star-forming region, and one of the most powerful in our galaxy, is the Karina Nebula. It's the equivalent of about 1,000 Orion nebulae. And then the familiar Alpha Centauri, Beta Centauri, and Crux and the Coalsack. And in the infrared, you see that Carina is just burning very brightly. And in fact, there are residuals that extend up from it, perhaps in the form of an outflow. Again, we don't really know. And lots of frothy material. So the complete tableau is kind of overwhelming in terms of, you know, what are we really seeing? So we're going to just have to surf this stuff and get down into the statistics. But already we can see that the strength of the froth is uniform in latitude. You know, it's a continuous carpet from the midplane all the way up to higher latitudes. That means that it scales with the smooth component that was divided out. Okay, so it's stronger near the midplane, just as the smooth component is stronger. And so when the smooth component gets divided out, it equalizes with the stuff at the higher latitude. And so the smooth component, as I tried to show you with that diagram, that strong midplane brightening is the result of viewing a disk of emitting dust from within it. And so that's what we're probably seeing with the froth. We're seeing that the froth similarly traces features throughout the disk. When you're at low galactic latitudes, the froth is from near and far. When you get to the higher latitudes, you're looking at froth, which is probably nearer. But basically, you're seeing the entire tableau of dust emission, including its variations throughout the galaxy. And Frank Verosi did this work. He looked at the spatial statistics, and I know that this is a busy graph, but basically this one's looking towards the galactic center. This is looking in the direction of the sun's motion, and this is looking towards the galactic anticenter. They all look the same, so I'll just talk about this one. The x-axis is basically the spacing from 10 degrees to 1 degree to 1/10 of a degree. And the y-axis tells you how much structuring is at those spacings. Okay, so it turns out that most of the structuring is at the largest spacings on the order of 1 to 10 degrees, okay? And then the power of the structuring gets less and less, and it's all very smooth in this log-log plot, and that's consistent with a power law with a slope of, which can be converted into a fractal dimension. Basically what we're seeing is self-similar structure. And that's what you see with the branching of trees. The trees branch into their initial branches, those branches branch, those branches branch, et cetera, et cetera. It goes on and on. So there's structure at all size scales. And this particular dimension for the fractal is 2.77. I think if it was 2.0, it would just be a smooth tableau. Okay. And that's basically seen in all directions. There does seem to be a change in the slope, as if maybe you're being shaped by some processes that involve, well, I'll get into those processes, but maybe more turbulent processes, more stochastic processes, they call it, at the shorter spacings. Okay. So here is where Bill Wall did some magnificent work. I'm just going to show one page, which takes us from 30 degrees to 90 degrees. So that's basically looking sort of along the sun's orbital motion. It includes the Cygnus star forming region right here. And Bill looked at tracers of other phases, like gas phases. And the green phase showed the most correlations. This is a map of correlations. And the green shows the correlations of the atomic hydrogen emission with respect to what we're seeing in the infrared. And the red is radio continuum from ionized gas. So that's where stars are scorching the gas and ionizing it, making it glow in the radio continuum. And there's also CO emission, a few regions of blue emission. And so that's tracing where the molecular gas matched up with the infrared gas, infrared emission nicely. So we saw a whole bunch of correlations, most with the H1. So the froth seems to be best associated with cool atomic gas clouds, but there's also strong correlations with these radio continuum emission enhancements. And so that's where the material, the froth, basically gets into, features, warm clouds ionized by high mass stars and possibly supernovae. And then finally, several correlations with the CO emission, which traces the molecular clouds. So that's basically what we found. And I just want to show this beautiful rendering by Frank Feroci. Did a better job looking towards the direction of our motion, the sun's motion. And it just shows this beautiful shell-like appearance. This just, begs further observations at higher resolution. These are big hunks of sky, 10 degrees or more. And so with telescopes, typical telescopes that Dick Lukey and others would have cannot even see a full degree of the sky. And so you would be sampling, smaller pieces. I like this rendering because not only does it show, excuse me, the Andromeda Galaxy, but it has this thing called like X. This X marks the spot, but what spot? And then finally, either this loop or that loop, I think it's this little curve, that's tracing a supernova remnant. the Cygnus loop, which Dick Lukey and other amateur astronomers know a lot about. They observe it during their star parties. So there's a lot of structure. There's perhaps too much structure to behold and to comprehend. But there are some key takeaways that we've been able to come up with. The froth, the dust, is structured as a self-similar fractal, which pervades the disk of the galaxy. And also there's anecdotal structuring. I talked about shells from prior star formation. And so this leads to the major question: what's producing all this structuring? What are the physical processes? So we can start off with just these photoionized nebulae, these pretty red H2 regions like the one behind my head. What happens is you have cold molecular gas. It's a cold cryogenic nursery. The stars get made, they collapse gravitationally, they get made. The massive stars shine brightly in the ultraviolet. The ultraviolet radiation rips the molecules apart, and then it rips the electrons off the individual atoms and heats up everything. Everything what was once just a few tens of degrees above absolute zero now are at 10,000 degrees. And just like a hot air balloon, there's expansion. And so some of the bubbles, like the head of Orion, could be just due to this expansion of the hot photoionized gas. Another possibility is that these same stars can blow mighty winds, not just when they're in their hot blue state, but also when they're in their red supergiant state, like Betelgeuse is now. And they can push things around. And then finally, the massive stars are doomed to explode as supernovae, and those will leave shell-like remnants as they interact with the ambient interstellar medium. So that's what the stars can do. But there's also just overall interstellar turbulence. And the turbulence is also self-similar. There's a cascade from the larger scales to the smaller scales. And so there's a possibility that interstellar turbulence is playing a role. And then just simple gravitational instabilities. The denser regions get ever more dense, and the emptier regions get ever more empty. And so what the balance of these various mechanisms are in constructing the froth, we still don't know. But wait, there's new data. And they include all sorts of data from all sorts of missions. Let's start with the optical. Here's the Lagoon Nebula, a nice binocular object, and the Trifid Nebula, like what's behind my head. And that's what you see in the visible, along with the Cat's Paw Nebula and the Lobster Nebula, which can be seen from the southern hemisphere. And if you're just interested in the stars that's inside these clouds, you could look in the near infrared. But if you were interested in the molecular gas and the dust associated with these nebula, you would look in the mid-infrared. And if you were interested in the dust clouds associated with the star-forming cores, you might look in the sub-millimeter part of the spectrum. So this is beautiful, much higher resolution data than what I've been showing to you before. And then there's the Planck mission. The Planck mission was intended to map out the cosmic microwave background. So that's the echo of the Big Bang. But they had to get the foregrounds characterized and subtracted off before they could get the cosmic microwave background. And so that is a wonderful thing if you're a galactic astronomer like me. And their highest frequency, shortest wavelength emission is at 350 microns. So that would be, I don't know, 3 hair widths. And it, again, is showing emission from this irradiated dust, but it's a beautiful, beautiful piece of data, well calibrated, et cetera, et cetera. So this is available to everybody, even rubes like me, through NASA's Skyview facility online. They also have imaged at multiple wavelengths, and these have revealed multiple phases. The dust from those around 350 microns. The molecules, I think it's associated with the carbon monoxide molecule, CO molecule. The ions, which is at a fairly long wavelength, low frequency, and that's why it looks a little fuzzy. The angular resolution isn't as good, but definitely worthwhile data. And then finally, the coronal. Here you have gas that's around 10,000 degrees associated with the massive star formation. Here, this is million-degree gas associated with supernova and other crazy events. So fabulous stuff. Moving up beyond the Milky Way, there's the Large Magellanic Cloud, which is a southern hemisphere object, alas, for us. But it has this bar, it's our companion galaxy, a bar of stars, and it might be a disk-like galaxy, but if it is, it's very ratty. But it has many, many star-forming regions seen in red because the hydrogen, after it gets its electrons ripped off, the electrons recombine and cascade down through the energy levels and emit this beautiful red color at a very particular wavelength. Highlighting this galaxy is the Tarantula Nebula, which is the equivalent of 1,000 Orion Nebulae. And inside that is the cluster, the R136 cluster, which is powering this nebula. So what would you see in the infrared? Again, it's more than you bargained for. The Tarantula Nebula is a very busy place, but there's also other very busy places which look like they've been cavitated here, and another one here. So this is a region, a galaxy that definitely merits further understanding in terms of the structure of its interstellar medium. And then we'll move on to the Pinwheel Galaxy, which is in the northern hemisphere, and it's 2.5 million light years away. And it's basically a raggedy spiral galaxy, about half the size of the Milky Way galaxy. And it has this region right here. It's called NGC 604. And that's about 500 Orion nebulae worth of star-forming matter. And in the infrared, again, courtesy of the Herschel satellite, you can see NGC 604 as a part of a raggedy spiral arm. And so this is a kind of a nice reminder that when we're looking through our own galaxy's disk, that some of the material is structured in spiral shapes, which we would not know because we don't have distance measurements to what we're seeing in the infrared. This is just a reminder. And then finally, if this wets your whistle, you might want to check out my book on the Milky Way, An Insider's Guide. That's a bit of a cruel joke that we are all insiders doomed to ponder and puzzle over the Milky Way and its structuring from the inside. We don't have an opportunity to see it from beyond. And then if you are interested in galaxies beyond the Milky Way, I can recommend Galaxies in the Cosmic Frontier. So I believe that is it. Yes, here's a plug for the Galactic Inquirer. If you have any interest in articles and videos, such as the one that I'm doing right now, please feel free to check it out. Okay, I think I'm done. Okay, I'm going to stop sharing. And thank you all for your attention. Let me stop sharing the screen. Oops. Okay, do we have any questions?
Yeah, I got one or two
Okay,
or three
Phil.
or four.
Oh my God. Good.
Yeah, actually, you've quit sharing the screen, and I wish you'd share the screen again, because I wanted you to show that 50 degree by 50 degree section of the sky with your froth again.
The pretty one?
I suppose they're all pretty.
The colored one?
No, actually, it's the gray and white one.
Okay, so that was 100 by.
Was it 100 by 100? Okay.
100 by 60. And where do you, towards the sun's direction of motion, this one?
Yeah, I think that was it. And then you expand it to this full screens.
Oh, okay, sure. There you go.
Yeah, maybe that's not the one.
Okay, well, we can move on.
Yeah, there was one where I saw something which was probably just an artifact, but it was an impressive looking artifact.
Well, you mean this finger of God?
No. There was something that looked like a huge circle in there, and I'm guessing that was just
well, let's go start at the beginning. Here you go. Here's looking towards the center.
Yeah, that's the one, actually. Yeah, you can see something that looks like a huge circle that goes around the left side, near the left there, and goes on the right as well. It's like it comes back on the right. You can see like this huge circle that goes all the around. It's like, I don't know if that whole thing is what, 100 degrees by 50, you said?
100 by 60.
100 by 60, yeah. Okay, so it looks like it's like 40-degree diameter circle. It looks.
This little line right
like an
here,
artifact or something.
This little line right here
there.
Is, I think, is a mosaicing artifact. This line right there.
But you see sort of like a semicircle on the left side there.
Left side, yeah, I know. I have no explanation for it. So it's worth revisiting, as I said earlier on.
Yeah. Another thing I was wondering, when you're showing your froth there, have you tried like reversing the scaling so that the dark becomes light and light becomes dark? Because then the holes become like peaks and the peaks become like holes. I mean, just.
Okay, I could try inverting. I remember that
I'm wondering what kind of statistics you get from that. That could be quite interesting.
I remember you did some tests to see whether objects like this or voids like this were artifices of the smoothing and the dividing out. And I think you came to the conclusion that no, they were real things, real diminutions. And if you look at the original, you will see it.
Yeah.
You can sort of see it right there.
Yeah. But what's in those holes could be interesting, right? So, I mean, just inverting the scale might be interesting.
Mm-hmm. Yeah, I got that written down. Yeah, I mean, I can play with this on my own with the limited software that I have, which is ancient. You know, everybody's moved on. You know, we lived in the days of IRAF and IDL, and now it's all Python and beyond.
But the noise. Have you tried doing maybe it's something I did a long time ago and I can't remember, it was so long ago, but did you do histograms of the pixels so that you can characterize the noise?
I think we did pixels for the noise. I think this is not noise, and that's because if you go from here and then you go back, you can usually find it in the original.
Yeah. Well, I don't think this is all noise, but the thing is you want to be able to know the level of the noise so that you can sort of ignore it, right?
Okay.
I mean, there's too much, there are systematic features there that it couldn't all be noise. That would all be very random, and it doesn't look very random. It looks like there's systematic structures there.
Right.
but it would be good to characterize the noise.
Yeah. So
and
that is kind of addressed here.
Right.
That this might be noisy.
Right.
At the highest resolution.
Right.
Smallest space.
Yeah. And you talked about these physical processes that could produce the structure. What would be interesting, and I don't know how you would do this, because you have to be able to somehow determine which physical process produced which structure. But if you could do that, you could sort of redo what I did, where I use color coding.
Yes.
And you could say, okay, this color represents this process,
right.
stellar winds, and this one represents, gravitational effects or whatever. And you could have, a multicolor image that would show you how these physical processes varied across the galaxy. And that could be extremely interesting. The problem is, how do you figure out which physical process is related to each structure? Right?
One thing you can say, that since the most common correlation was with the neutral hydrogen, the atomic hydrogen, that means that the structuring, whatever it is, was not very destructive. It allowed atomic hydrogen to remain atomic hydrogen. It didn't rip it apart.
Yeah.
I think that's in our report somewhere.
You have lots of questions in the chat there.
Oh, I do. Where's the chat? Hold on. I'm having trouble seeing the chat. Oh, more. There we go. Thank you. Okay, I'm going to start at the top. Don't forget to introduce the speaker. That's me. Love that photo from Pacholka. Yes, I'm sure he'd be happy for you to buy it. Areas of the galaxy burning out as they convert hydrogen. Are there sources of new molecular hydrogen that allows galaxies like ours to renew themselves? Our galaxy is not forming stars at the rate that it was 12 to 10 billion years ago. We're pretty sure about that it was more active in the past. And we can see that in a variety of ways. But we seem to be on a slow burn. We still have about 1 billion solar masses worth of star-forming gas out of 100 billion solar masses overall. I think that's about right. So we're not dead yet. Whether or not there are new sources of molecular hydrogen, well, there's always the possibility of infall from other galaxies. And there is a galaxy that is now falling into the Milky Way, even as we speak, in the direction of Sagittarius. So that's one way to fuel the galaxy. And then in 4 billion years, the Milky Way and the Andromeda galaxy, they'll collide. They're supposed to be on a collision course. So that's a hell of a way to renew your star-forming activity.
Also processes in our galaxy where the atomic hydrogen is brought together on dust grains, for example, and forms new molecular hydrogen.
Right, the conversion of atomic gas to molecular gas, which you probably know more about than I do, because you were working working in radio astronomy for a while, right?
Yeah, and there are about 10 billion solar masses of gas in our galaxy.
10 billion. Thank you. I sit corrected. Okay. Brewster says all the hydrogen that there will ever be formed in the Big Bang. Buy it now? Yeah, it's a good investment. It's good. What will be the long-term evolution of the galaxy? Barring that collision, for the next billion or so years, I think it's just going to tootle along in the disk like it's been going. There aren't any major galaxies about to fall into the Milky Way other than that Sagittarius dwarf. There are clouds. There are high latitude clouds, high velocity clouds is what they're called, and they could possibly fall in. The large and small Magellanic clouds may eventually fall into the Milky Way. And so could get a new spurt of star formation. And Brewster is dropping off. That was the last comment, last chat. Any other questions? Feel free to unmute yourselves if you have any questions. Okay. Well, if not, I thank you for your attention. Again, this will be on Doc Waller's Earth and Space Reports YouTube channel, and also will be aired on our local cable TV station, 1623 Studios. So I guess I will say good night. Thank you.
Thank you.
Thank you. Take care.
Excellent.
Take care. All right. Stop sharing. And stop recording.